Algebras. Welcome to your Chapter 7 Lesson 4 notes, all about factoring completely. We are actually going to have notes on factoring completely twice, but this is the beginning, right after we have done three main types of polynomial factoring, and I'm going to list those momentarily. So this is the first time we're going to be talking about this term, factoring completely. Before I get into this, I want to remind you that factors are multiplied, as in the past, pieces. So these are 2, 3, 4, however many pieces have multiplied together to give me my current product. Factors are going back and figuring out what were the things that multiplied together. Okay? Now, the three types of polynomial factoring we have done so far in Chapter 7 have been GCF, which of course stands for greatest common factor. So we did greatest common factoring, undistributing basically. Then we did DOTS, which stands for difference of two, and I like to say the word perfect squares, but of course, to make it a nice dots, difference of two squares, right? And lastly, we had trinomial into binomial factoring. Okay, typically we just call that trinomial factoring, but I just want to be clear as to what its results were. Okay, so it's a nice little flow chart we can ask ourselves when we look at a polynomial. The first thing we ask ourselves, is there a GCF, right? Is there a GCF when you look? Always look for a GCF before any other type of factoring. I just enjoy this little flow chart, right? Is there a GCF? If the answer is yes, take it and then check the leftover. And that's actually the discussion we're going to have today, this then check the leftover. But is there a GCF? No. Are there two terms? If the answer to that is yes, it's probably dots, difference of two perfect squares. Okay. If the answer is no, hopefully there's three terms because we know how to deal with that. And if the answer is yes, then we're going to factor it into two binomials. If the answer is no, at the level we're at, that's the key. The level we're at, it's not factorable right now. Okay. So if there's not two or three terms for now, it's not going to be factorable. Okay. That will change when you get to algebra 2, possibly even geometry. But for right now, these are the questions you want to ask yourself. Okay. Remember, we get dots if you have a perfect square minus a perfect square. So at this point, after we did the lesson 1 through 3 review, we should be able to look at a polynomial and be able to tell, oh, yes, there's a GCF. Let me pull that out. Or, oh, yes, there's two terms. There is a perfect square minus a perfect square. Let's factor that into two binomials. Or, oh, there's three terms. Let's look at the end number and see what are the factors that give me this number that also add to get the middle. That's how we handle factoring at this point. And that all comes into play right now. So the reason that I went through all of that again is because when you factor completely, you are going to run into all of these potential opportunities of factoring. Okay. So real quick, just a couple more examples of general factoring. This line is all GCF factoring. This line is all dots factoring. And this line is try to buy factoring. That's what I'll call it. Right? Trinomial into binomial. Okay. So let me do one from each section and then let you try one more time so that you're then ready for factoring completely. So I'll start right here because typically the having variables can be a little challenging for people. in GCFs, right? So greatest common factor is what can all the current terms evenly divide by? I know that 15 and 30 both evenly divide by 15. I know that x cubed and x squared both evenly divide by x squared because it's the biggest number of x's I can take out of everything present. So my GCF, my greatest common factor, is 15x squared. And then after I write my GCF, I make an empty set of parentheses behind it where I can put my leftover. My leftover is take the original polynomial, now divide each term by the GCF. 15 divided by 15 cancels out to a 1. X cubed divided by x squared cancels out to an x to the first, or just an x. Negative 30x squared, so negative 30 divided by positive 15 is a negative 2. X squared divided by x squared cancels out to a 1. Negative 2 times 1 is still just negative 2, so it kind of absorbs that 1. So if things cancel out to a 1, they get absorbed by whatever that number is that's already present. If everything cancels out to a 1, then what's left is a 1, and that's what you write down. Okay? So that's our GCF. You know what? Let me just do this one too, because the letters can confuse people. It's got to be divisible in all the terms. So if you look at all the numbers, 2 and 4 and 8 are all evenly divisible by 2. You can't say they're all evenly divisible by 8 because 2 isn't. Okay? Do they all have an A, at least one A present? Yup. And that is the most A's I can pull out of everything. Do they all have at least one B present? Yup. Do they all have at least one C present? Yup. So that is all part of the GCF. Now I'm making myself a big empty set of parentheses behind for the leftover. Okay? Now each term gets divided by the GCF. If a term is divided by itself, like in the case right here, only a 1 is left. 4 divided by 2 is 2. A squared divided by A is an A left. The B's cancel out to 1. The C's cancel out to 1. Negative 8 divided by 2 is negative 4. The A's cancel out to 1. The B's have a B, one B left over, or B to the first left over. And of course, the C's cancel out to a 1, so I can stop right there and I'll just get rid of the empty other parenthesis that was over here a little prematurely placed, right? Thought I'd have a lot more in my leftover. But I want you to see when factoring by GCF, the number of terms in the original polynomial is the number of terms you will have in your leftover. For difference of two perfect squares, you have to have a perfect square minus a perfect square. So both terms have to be perfect squares and you have to be subtracting them. So in the case of number 5, z squared is a perfect square, 225 is a perfect square, and I'm subtracting them. That always factors the same way. Make 2 empty sets of parentheses to put 2 binomials in, okay? Take the square root of the front term, square root of z squared is z. That square root now goes in the fronts of each binomial. Go to the back term, take the square root of 225. Square root of 225 is 15. That square root now goes in the backs of each set of parentheses, and then put different signs between them. It does not matter which binomial gets the plus and which gets the minus, because we're looking at the same numbers, but you have to have one of each, because that middle has canceled out in the trinomial. That's essentially what has happened here and what we've discussed. And so even with bigger situations like over here, where you've got 4r to the 4th, well, any even exponent is itself a perfect square. So 4 is a perfect square, r4th is a perfect square. Then you got 25s squared is a perfect square, and you're subtracting them. So you know that you make 2 empty sets of parentheses. Take the square root of 4r to the 4th. That would be 2r squared in the fronts of both sets of parentheses. Take the square root of 25s to the 2nd. That's 5s in the backs of both parentheses, and different signs between them. Again, because multiplication is commutative, it does not matter which order I write my two binomials that are multiplying together. What matters is having the right terms with the right signs in those binomials, in each of those binomials. Okay, because multiplication is commutative. It doesn't matter what order I multiply in, I'll get the same answer either way. And where that plays in, again, is trinomial into binomial factoring. When you have a trinomial, make sure it's in standard form. So your constant term is at the end. We call that the C term. And your B term, the middle term here, that number and sign will drive us as we go. So this number right here, the end number, we think, what are the things that multiply together to give me 10? So you got 10 and 1 and 5 and 2. Now, which combo of factors also adds or subtracts to give me -3? Well, that's going to be 5 and 2 because 5 minus 2 is 3. So here's how I'd work that sign-wise. I make my two empty sets of parentheses. I look at what my variable is, and I get that in the fronts. Now, that 10 in the back had said only pick things that multiply together to give me 10. So that's how I could narrow it down to 1 and 10 and 2 and 5. 2 and 5 is the only combo that will add or subtract to give me 3, and that's if they subtract. Now, I already knew they would have to subtract because if the end number is negative, these have to be different signs. How I figure out which sign is which is the bigger of the two factors has the same sign as the B term. What's bigger, a 5 or a 2? 5 has to have the same sign as the middle, so it's negative, which because these have to be different signs, leaves the 2 to be positive. If your C term is positive, the two signs in the binomials will be the same. You will be adding to get the middle, and those two signs in the two binomials are the same sign as the B term, okay? Because the bigger factor always has the same sign as the B term. So if these have to be the same, then you have to be the same as the B term, right? So what are some potential factors of 20? Well, 20 and 1, always the number and 1. And then 10 and 2. Oh, wait. 10 and 2 will add up to 12. Will 4 and 5? No, they add up to 9. So there we are. Okay, let's try it. So we've got x here, 10 and 2. And the bigger factor is 10. It has to have the same sign as the middle, but because the end term is positive, both of these have to have the minus sign anyway, so there we are. We're good. Pause it right here, and you try those 3 that I left, 1, 4, and 7. Give those a go, see how it is, and then we'll move forward. All right, check those. Make sure you got those right. Because like I said at the beginning, factoring completely is you may have to use GCF and dots, or GCF and trinomial to binomial, or trinomial to binomial and dots. It could be some combo of these. But factoring completely means no potential factors can be left. Everything has to be out in all of its multiplied pieces. Now, in the old way we were looking, everything has 2 multiplied pieces. It's this GCF times this leftover, or it's this binomial times this binomial, or it's this binomial times this binomial. So far, all I've got are 2 factored pieces. Well, when factoring completely, we might have 3 factored pieces out. We might have 4 factored pieces out. Everything potential factoring needs to come out. When your directions say factoring completely, that is your indication to make sure this isn't going to happen just once. You've got to make sure you pull all the potential factors out, okay? So if my directions say factor the given polynomial completely, then I know I'm going to be factoring more than once, okay? I just know it. That's what's going to happen. So what I'm going to do here is I'm going to use this procedure with all of these examples as I go. The first thing I always look for is a GCF. I mean, that's the first thing I always look for anyway. Okay, so when I look at this trinomial, I'm looking for, is there a common term between all of these things? And the answer right now is no, there's just not. So next thing I say is, oh, well, this is a trinomial in standard form. So let's look at the constant term, 90. Think of some potential factors of 90, things that multiply together to give me 90, that can subtract a negative 90 to give me a positive 1. Well, to get 1, that means numbers next to each other on the number line, right? So what's 9 times 10 is 90, and 10 minus 9 is 1. There's my factors. So I look at my front variable, and instead of just an m squared, this is an m to the 4th. That means that when I go to make my empty sets of parentheses and put my m, it's going to be an m squared in both of these binomials. Okay, that makes sense because m squared times m squared gives me that m to the 4th right there. Okay. Now we just said that 9 and 10 multiply to give 90, but subtract to give 1. Now, what's bigger, a 9 or a 10? 10. And what's the what's the sign of the b term? It's a plus, so that means 10 has to be a plus. And if your n number is negative, then this has to be the other sign. Normally, you would think, good, I'm done. But I see something here. The direction said factor completely, so I know I've got more factoring to happen, and I also see a perfect square minus a perfect square. So this is dots now. So now I think, okay, that factors to be 2 empty sets of parentheses, but wait, I've got this guy back here. It's not dots back here. So I just bring this guy down to the next line. I don't have to refactor him. There's no GCF in there. It's not dots. He is as factored as possible, this m squared plus 10. Sorry that I was gendering him, but whatever, right? That thing is as factors as it goes. But not, m squared minus 9, that can factor further, so I do it. Square root of m squared is m. Okay, m's in the fronts of the two binomials. Square root of 9 is 3, so 3 is in the backs of both binomials and different signs between them. Now look, there's no GCFs left, there's no dots left, there's no trinomials left. We're done. But look how many things we have in our final answer, 3. Because when factoring completely, there'll be more than 2 factors left. Okay, let's try that again. In example 2, I should immediately see a GCF. Okay, both 4 and 64 are evenly divisible by 4. So that's where I start. Bring out a 4 as a GCF. Well, 4v to the 4th divided by 4 leaves a 1v to the 4th, or just v to the 4th. Negative 64 divided by 4 is a negative 16. So there's my leftover. So I got my GCF in the front, got my leftover here. Look at my leftover. It's a perfect square minus a perfect square. It's dots. So I can factor it again. Okay. Bring down your factor that's not going to get messed with because it's all done. Make 2 empty sets of binomials. And we've got, let's see, square root of v to the 4th is v squared. So that's going to go in the fronts of both of my binomials. Square root of 16 is 4. So that's going to go in the backs of both of my binomials. And then, of course, different signs between them. Check one last time. Look at all the stuff in the binomials. We know that the GCF is okay. Can't be factored further. Not dots. No GCF. We're good. Dots. Perfect square minus perfect square. That can factor one more time. So this answer is going to have 4 factors. Bring down the factors that cannot be factored further, right? Don't have anything left in them. But since this is difference of 2 squares, I again make 2 empty sets of parentheses, and I again take the square root of the front term and put it in the fronts, take the square root of the back term and put it in the backs, and put different signs between them, and phew, now I'm done. Now I'm good. Now I'm done. Now I'm good. Okay, so that, notice, took longer to get to the final factored piece. So sometimes it will. What I do want to tell you is when you see a binomial, that should be kind of a red alert to look for dots. Look for difference of 2 squares when you see a binomial. Always be on the lookout for a GCF. Always be on the lookout for dots. Okay? If you got a trinomial, that's how it will factor at this point in our work. Because we're in Algebra 1, if I'm giving you these trinomials for factoring completely, they'll be factorable. Keep going. Couple more examples.
Excuse the interruption. The BTW after school program is canceled for today.
I'm gonna leave you. Sorry, there's an announcement. I'll probably edit this out. I'm going to leave you a few examples to try, but I'm going to do a couple of them, okay? Because sometimes we run into what we just saw, you know, where there was 4 at the end. Sometimes we run into the other thing we saw where there's just 3 at the end. So there were only 2 factorings that happened. So I'm going to show you a little bit of both, okay? All right, let's see here. Let's go to, you know, why don't we do the odds and I'll leave you the evens. How's that sound? Okay. So let's see. Number 3, ooh, there's no GCF, but I notice a perfect square minus a perfect square. So that will factor into 2 binomials. Square root of 16 is 4 for the fronts. Square root of c to the 4th is c squared in the backs, and different signs between them, and I see another dots. 4 minus c squared is a perfect square minus a perfect square. So I do that process again. Any factors that can't be factored further, just rewrite in the final answer. Bring them down, rewrite them for the final answer. Square root of 4 is 2 for the fronts. Square root of c squared is c for the backs, and different signs between them. Check to make sure all the GCFs and dots are gone. Okay. Now, when I've got to the 4th power, that kind of gives me a hint that like, oh, this will probably end with a dot somewhere, right? So this is a trinomial. What are the factors of 18 that will add to give me 11? Okay, that's going to be 9 and 2, right? So y to the 4th is the start, y squared is the middle. That means we have a y squared here and here. We said 9 and 2. The bigger factor always has the same sign as the middle, so this is going to be negative because the middle is negative. But also, since the n term is positive, this has the same sign, these 2 factors, same sign inside. And I should immediately have a little spidey sense of dots, right? Because I had y squared is a perfect square, and I'm subtracting in both binomials. Dots. Not dots, not a perfect square. So this factor will just come down to the next line. But this one will factor to become y minus 3 and y plus 3. And then bring down the y squared minus 2. And you are all done. No more GCFs, no more dots. Number 7, all those things are divisible by 5. So there's a GCF right off the bat. So let's factor that guy out. Divide everything by 5. And here's where we end up. Okay, well now this is a factorable trinomial. So bring down that GCF. Now 2 empty sets of parentheses. And let's see. It started with a v to the 4th, and we've got a v squared in the middle. So that means there's going to be a v squared in the fronts of each of these. The factors of 8 that add, because 8's positive, to give me a negative 6 in the middle. So 4 and 2. 4 times 2 is 8. 4 plus 2 is 6. And because they have a positive 8 at the end, where same sign in my binomials, same sign as the b term, which means they're both negative. And you can see right there, you got a perfect square minus a perfect square. Not here, because 2 is not a perfect square. So bring down the 5, make 2 empty sets of parentheses, bring down the v squared minus 2. Square root of v squared is v. Square root of 4 is 2, and different signs between them. And woof, took a little bit, but we got there. (27) and negative 3x squared, both evenly divisible by 3. Leaves you 9 minus x squared. Okay, dots. So bring down the 3. Then 2 empty sets of parentheses. Square root of 9 is 3. Square root of x squared is x. And different signs between them. Done. No more dots. no more GCFs. Okay, so watch kind of how that's going. I'm just gonna zoom out so you can see all of my examples from this page on one page. Oh, look, hope that's obvious that there's an A in all three terms, right? So A and then x squared plus 7x plus 10 is the leftover. That is, of course, a trinomial that factors to become two binomials. And the factors of 10 that add to give me 7 are 5 and 2. So since 10 is positive, these have the same sign, and it is the same sign as the middle. We're done. No dots left, no GCFs left, no trinomials left. We're good. I want you to try the evens on your own right now and then check your answers with mine real quick. So pause here and check those answers, and we'll come right back. Okay. Check your answers on the evens here. See how you did. You always want to be on the lookout for a GCF first. Okay, so always pull GCFs out first because the leftover is probably a factorable trinomial or a factorable difference of two squares. Okay, so when you've got a binomial, just check for dots each time. Okay, so perfect square minus perfect square. So that's the key. That's the thing that people kind of forget about. Like on number 8, for example, when you factor this into these two pieces, x squared plus 7 and x squared minus 1, you might forget that one's a perfect square and this is a perfect square minus a perfect square, so it's got to factor further. Okay, so you want to be kind of on the lookout for dots, which means you really want to know perfect squares. You really want to know what your perfect squares are. You really want to be able to identify perfect squares quickly. Okay? All right, guys, good luck with this. Lots of practice with this. Remember, if the directions say completely, there will be more than one factoring. So be on the lookout. Follow the flow chart. Ask the questions. And if you have anything you want to ask me, I am here to help. Let me know. Good luck. Have fun with your factoring. Bye, guys.